Today, we're going to dive into the world of trigonometric identities, which are essential tools for anyone studying AP Precalculus. Our topic for today is equivalent representations of trigonometric functions. By the end of this video, you will be able to rewrite trigonometric expressions using the Pythagorean identity and the sine and cosine sum identities. Our learning objectives are: first, to rewrite expressions using the Pythagorean identity; second, to rewrite expressions using the sine and cosine sum identities; and finally, to verify other trigonometric identities using these tools. These skills will not only help you solve more complex problems, but also deepen your understanding of how trigonometry works. They are incredibly useful for expressing trigonometric functions in ways that make equations easier to solve. Our first major objective is to learn how to manipulate trigonometric expressions using the Pythagorean identity. So, we'll start with the objective: rewrite trigonometric expressions in equivalent forms, using the Pythagorean identity. This fundamental identity comes directly from the Pythagorean theorem, applied to a unit circle. Imagine a right-angled triangle inscribed within a unit circle, with its hypotenuse being the radius. The coordinates of the vertex on the circle are cosine theta, sine theta. By the Pythagorean theorem, x squared plus y squared equals 1 squared. Substituting cosine theta for x and sine theta for y, we get our identity. This gives us the most important trigonometric identity. Sine squared theta plus cosine squared theta equals 1. This identity is true for all values of theta. From this single identity, we can derive two others that are just as useful. We can do this by dividing the entire equation by a trigonometric function. First, let's divide every term in the identity by cosine squared theta. Dividing sine squared theta by cosine squared theta gives us tangent squared theta. Cosine squared theta divided by cosine squared theta is 1, and 1 divided by cosine squared theta is secant squared theta. This gives us our first derived identity. So, tangent squared theta plus 1 equals secant squared theta. Now, let's try dividing the original identity by sine squared theta. This time, sine squared theta over sine squared theta is 1. Cosine squared theta over sine squared theta is cotangent squared theta, and 1 over sine squared theta is cosecant squared theta. This gives us our second derived identity. So, 1 plus cotangent squared theta equals cosecant squared theta. These three identities, the original Pythagorean identity and these two derived forms, are the cornerstone of many trigonometric manipulations. Now that we know the identities, let's see how we can use them to rewrite expressions in a more useful form. Let's work through an example. Suppose we have the expression 1 minus cosine squared of theta multiplied by cosecant of theta. The goal is to simplify this expression. First, let's look for any part that resembles one of our identities. You'll notice the term 1 minus cosine squared of theta. Recall our first Pythagorean identity. Sine squared theta plus cosine squared theta equals 1. If we subtract cosine squared theta from both sides, we find that sine squared theta is equivalent to 1 minus cosine squared theta. This is a perfect substitution opportunity. We can replace the term in our original expression. Substituting sine squared theta for 1 minus cosine squared theta, our expression becomes sine squared theta times cosecant theta. We've simplified it, but we can go further. We should try to express everything in terms of sine and cosine. Remember the reciprocal identities. The cosecant of theta is the reciprocal of the sine of theta. In other words, cosecant theta equals 1 over sine theta. Let's substitute that into our simplified expression. We now have sine squared theta multiplied by 1 over sine theta. This can be rewritten as sine theta times sine theta, all over sine theta. We can see that a sine theta term cancels out, leaving us with our final simplified answer, sine of theta. So, the complex expression we started with is actually equivalent to just sine theta. We successfully rewrote a trigonometric expression using the Pythagorean identity. Let's look at another example that uses a different form of the Pythagorean identity. For our second example, let's rewrite the expression cosine squared of theta plus 1 all over secant squared of theta minus 1. Again, let's scan for any parts that look familiar. Take a close look at the denominator, secant squared of theta minus 1. Recall our first derived Pythagorean identity. Tangent squared theta plus 1 equals secant squared theta. If we subtract 1 from both sides, we get that tangent squared theta is equivalent to secant squared theta minus 1. Now we can make this substitution into our expression. Our expression becomes cosine squared theta plus 1 divided by tangent squared theta. The numerator, cosine squared theta plus 1, doesn't immediately match a Pythagorean identity. This is a common situation. When in doubt, a great strategy is to rewrite everything in terms of sine and cosine. This is always a safe bet if you're stuck. We'll leave the cosine squared in the numerator for now. The tangent squared theta in the denominator can be rewritten as sine squared theta over cosine squared theta. Now we have a complex fraction. To simplify, we multiply the numerator by the reciprocal of the denominator. This gives us cosine squared theta plus 1 multiplied by cosine squared theta over sine squared theta. We can distribute the cosine squared theta in the numerator. This gives us cosine to the fourth theta plus cosine squared theta all over sine squared theta. While this is an equivalent form, it's not particularly simple. We've hit a small roadblock. Let's go back and try a different approach. What if we simplified the numerator first, before substituting the denominator? This shows that sometimes there's more than one path to the answer. Let's restart with our original expression. We start over with the original expression. Let's simplify the numerator first. The term cosine squared theta plus 1 isn't an identity itself. However, we can look for ways to create one. What if we add and subtract 1 from the numerator? This gives us cosine squared theta minus 1 plus 1 plus 1. Rearranging this, we get negative sine squared theta plus 2. Now let's use our earlier denominator substitution, tangent squared theta. Our expression is now negative sine squared theta plus 2 all over tangent squared theta. Once again, let's write everything in terms of sine and cosine. We have negative sine squared theta plus 2 divided by sine squared theta over cosine squared theta. Let's split this fraction into two parts. We have negative sine squared theta over tangent squared theta plus 2 over tangent squared theta. Let's simplify each part. The first part becomes negative cosine squared theta. The second part becomes 2 cotangent squared theta. This gives us our simplified expression, negative cosine squared theta plus 2 cotangent squared theta. This example highlights a critical point. There isn't always one direct path. If you get stuck, try a different manipulation or simplify a different part of the expression. Rewriting everything in terms of sine and cosine is a reliable strategy to fall back on. Now, let's move on to our second set of powerful tools, the sine and cosine sum identities. The objective here is to rewrite trigonometric expressions using these sum identities. These identities tell us how to find the sine or cosine of a sum of two angles, alpha and beta. The sum identity for sine is sine of alpha plus beta equals sine alpha cosine beta plus cosine alpha sine beta. You can remember this with the phrase sine cosine cosine sine. The sum identity for cosine is cosine of alpha plus beta equals cosine alpha cosine beta minus sine alpha sine beta. Notice the sign change. You can remember this with cosine cosine sine sine, with the opposite sign. From these two, we can derive several other very useful identities. First, the difference identities. For example, to find the difference identity for cosine, we can think of cos alpha minus beta as cos alpha plus meta beta. By substituting negative beta into our cosine sum identity, we use the fact that cosine is an even function and sine is an odd function. This gives us the cosine difference identity, cosine of alpha minus beta equals cosine alpha cosine beta plus sine alpha sine beta. The sine is the opposite of what's in the parentheses. Similarly, the sine difference identity is sine alpha cosine beta minus cosine alpha sine beta. For sine, the sign is the same as in the parentheses. These are incredibly useful, for example, to find the exact values of trigonometric functions for angles that aren't on the unit circle. Imagine you need to find the sine of 75 degrees. This isn't a standard angle, but we can split it into a sum of two standard angles, 45 degrees and 30 degrees. Then we can use the sine sum identity. This is a very powerful application of these identities. By rewriting the angle, we can find its exact trigonometric value. Beyond difference identities, the sum identities also allow us to derive the powerful double angle identities. Double angle identities are simply sum identities where the two angles are the same. Let's start with sine of 2 alpha. We can write sine of 2 alpha as sine of alpha plus alpha. Using the sine sum identity, we replace both alpha and beta with alpha. sine alpha cosine alpha plus cosine alpha sine alpha. Since addition is commutative, this simplifies to 2 sine alpha cosine alpha. This gives us our first double angle identity. Sine of 2 alpha equals 2 sine alpha cosine alpha. Now let's derive the double angle identity for cosine. Cos 2 alpha. Again, we write cos 2 alpha as cos alpha plus alpha. Using the cosine sum identity, we replace both alpha and beta with alpha. This simplifies to cosine squared alpha minus sine squared alpha. This is the first of 3 forms for the cosine double angle identity. The other 2 come from substituting the Pythagorean identity sine to squared alpha equals 1 minus cos squared alpha, or cos squared alpha equals 1 minus sine to squared alpha. Substituting for sine squared alpha gives us 2 cosine squared alpha minus 1. Substituting for cosine squared alpha gives us 1 minus 2 sine squared alpha. Each form is useful in different contexts. So, just to recap, these are our main double angle identities, all derived directly from the sum identities. Remember them well. Our final objective is to combine these tools to verify more complex trigonometric identities. This means showing that one side of an equation is equivalent to the other side. Learning Objective 3. Verify trigonometric identities. A common strategy for proving these is to start with the more complicated side and work to simplify it to match the other side. Let's look at an example. Verify the identity cos squared x minus sine squared x equals 2 cosine squared x minus 1. We can see that the left side is the first form of the cosine double angle identity. The right side is the third form, so we need to show that we can get from one to the other. We'll start with the left-hand side, cos squared x minus sine squared x. We want to eliminate the sine squared term and replace it with a cosine term to match the right side. We'll use the Pythagorean identity. We know that sin squared x equals 1 minus cos squared x. We'll substitute this into our LHS. Be careful with the parentheses. The substitution gives us cos squared x minus the quantity, 1 minus cos squared x. Now, let's distribute the negative sign. This becomes cos squared x minus 1 plus cos squared x. Finally, we can combine the like terms. We have 2 cos squared x terms, so our expression simplifies to 2 cos squared x minus 1. We have successfully shown that the left side is equal to the right side, thus verifying the identity. We used a Pythagorean identity as our key step. Let's try one more verification example, this time using a sum identity. We want to verify the identity sin of x plus pi over 2 equals cos of x. Here, the left-hand side is clearly more complex. It's a sine sum. The right-hand side is a single trigonometric function. This is a classic case for starting with the LHS. Let's apply the sine sum identity to the left-hand side. Remember, sine of alpha plus beta equals sine alpha cosine beta plus cosine alpha sine beta. Here, alpha is x and beta is pi over 2, so we have sine x cosine pi over 2 plus cosine x sine pi over 2. Now, we need to know the values of sine and cosine for the angle pi over 2, which is 90 degrees. We can recall this from the unit circle. At pi over 2, the coordinates on the unit circle are 0, 1. Remember that cosine is the x-coordinate and sine is the y-coordinate. So cos pi over 2 equals 0, and sine pi over 2 equals 1. Let's substitute these values back into our equation. We get sine of x times 0 plus cosine of x times 1. Now we simplify. The first term, sine x times 0, is just 0. The second term is cosine x, so the left-hand side simplifies to cosine of x. This is exactly what the right-hand side of our identity was. So, we've successfully verified it. We've shown that adding pi over 2 inside the sine function results in a phase shift that transforms it into a cosine function. Let's quickly recap what we've covered today. We explored the world of trigonometric identities, which are fundamental to AP Precalculus. We started with the foundational Pythagorean identities. First, sine squared plus cosine squared equals 1. From there, we derived 2 other forms, tangent squared plus 1 equals secant squared, and 1 plus cotangent squared equals cosecant squared. We then moved on to the sum and difference identities for sine and cosine. These powerful formulas tell us how to break down the sine or cosine of a combined angle. We also saw how they can be used to calculate exact values for angles that aren't on the unit circle. And finally, we saw how the sum identities lead directly to the double angle identities. These identities, particularly the three forms for cosine, are invaluable for solving equations and simplifying expressions. We practiced rewriting and simplifying expressions, and most importantly, we learned how to use these identities to formally verify other trigonometric identities. The key strategies are to simplify the more complicated side, and, if you're ever lost, to express everything in terms of sine and cosine. Mastering these identities will be a cornerstone of your success in AP Precalculus. Keep practicing, and you'll become an expert in manipulating and simplifying trigonometric expressions. Thank you for watching.